lectures. We have lectures about self-interception, local types. So we had yesterday some introduction, and today we have something new. So please.
Yeah. Thank you. So maybe I will begin by recalling some results that I introduced yesterday. First, we have seen the definition of occupation measure and local time. So if we consider a stochastic process xt, the occupation measure is defined by this formula, and it measures the time that the process spends in some Borel subset D. And if this measure has a density, then we call this density the local time of the stochastic process. There is also another approach to define the local time by using some kind of approximation. So if we have a function phi from Rd to which is positive, and with integrate it to 1, we can construct this family of function which has good properties in terms of convolution, and it converges weakly to the Dirac delta measure 0. So if the limit of the following integral from 0 to 1 phi epsilon xt minus u dt converges or exists in some LP sense, then the limit is also called the local time of the stochastic process. We have seen also how to derive this definition from the first one through the occupation formula, and also we have seen some criteria how to check the existence of local time for general stochastic processes. The first criteria here, it is based on the idea that finite positive measure has a density if its Fourier transform is square integrable, and in such case the density is square integrable. So if we write the Fourier transform of the occupation measure and write this condition of square integrability, we exactly find this multiple integral here of Rd and 0, 1, 0, 1 and so on with the expectation. So it is enough to check that this integral is finite, and so we have a local time for the stochastic process. There is another also criteria that can be used, but for central Gaussian processes. So if we consider the covariance matrix BST of the vector x of s and x of t, and we define this approximation with this specific family of function here given by these Gaussian densities here, then we have the following criteria that this family of integrals converge in epsilon tends to 0 in the L2 sense if the following integral is finite. Again, it is a simple condition. We just need to compute the covariance matrix and compute its determinant and check if it is integrable in this with the square root in the denominator.
So your second criteria, I guess, is the corollary of the first criteria. Right? You just need to check that the condition you put in the first one. Yes, the first, yes.
Yeah. I think it can be derived from this one, but it can also be obtained in in an independent way. I even explained the idea of the proof. It is based on if we want to show that something belongs in L2 sense, it is enough to prove that the expectation. So if we want to prove that epsilon converges to something, it's in R in L2 sense, it is enough to show that the expectation.
Right.
Yeah,
Right.
there's a limit between epsilon and epsilon.
I just want to say this is, you know, is a consequence of the first criteria. If you, because in the case of the Gaussian, it's very easy to check that characteristic function you put in your first criteria.
Yes. Okay. Honestly, I did not check but I think it can be done, since if the process is Gaussian, then there's a characteristic function here. It will be yes, and then if integrated over RD, it will give us the covariance with the square root in the denominator. So if we have this, then okay, yes, we have the finiteness of this integrator. Okay. Of course, there are other criteria to prove the existence of the local time, but okay, I just have chosen these one for they are simple to check. Some sense. Today I will speak about self-intersection local time, and I will begin by speaking about multiple points of the Brownian motion. Again, if we consider a d-dimensional Brownian motion, and a point of self-intersection multiplicity k, it has a point of self-intersection multiplicity k if we have t1 k times different times, such that bt1 equal to bt2 equal to bt. Of course, these are multiple points that you may have seen before. If you have any curve, okay, if you have any curve of a function from 0, 1 to RD, then you can define multiple points. For example, this one is a double point. It is visited twice by the curve. This one is a triple point. It is visited 3 times by the curve. Okay? We define points of multiplicity k in the same way as given in this definition. Okay? Of course, maybe one have to be honest about some point. Here, according to this definition, this is a multiplicity at least k, because the same point maybe is visited by some other instant. But okay, we say that the multiplicity is k.
At least.
Yes, it is the true mean is at least k. Okay. Okay. And now the following theorem, which was proved by Dvoretsky and Doss and Capitani in a series of papers in the 50s, tells us that the Brownian motion, the d-dimensional Brownian motion, almost surely has points of self-intersection of any multiplicity if the dimension is equal to 1 or 2. But only has points of self-intersection of multiplicity 2 if the dimension is equal to 3. And does not have points of self-intersection if the dimension is greater or equal to 4. It is a strange dependence with respect to the dimension, and we see that in dimension 1 or 2, we can find points of any of self-intersection for any multiplicity. In dimension 3, there are only points. You can only find points of double points, but you cannot find triple points. In dimension greater or equal to 4, the Brownian motion is an injective function. It has no points of self-intersection. Okay. And now, the local time is, we could,
I may be wrong. I was not a person of good memory, but I remember this result. But I thought that's perhaps for the mutual intersection. That's the truth, certainly.
you mean when we consider dependent Brownian motion?
For example, if you have independent Brownian motions,
Yeah.
one dimension is fine, no matter how many you put together. Two dimension is also fine.
Fine forward. Fine forward.
To have intersection, and just like what you say here, if you basically what I mean is, if you just change this statement to independent
Brownian
motions,
I think this
that should be true, and they also call this name, but I don't know if this when you talk about self-intersection, if that's still true.
I'm sorry, did not understand the last point, but
the point is, if this is a mutual, if you are talking about mutual intersection for local time, and this statement, I know this statement is
Yes.
true, and also that's a name after those three guys.
yes, but also for one single Brownian motion,
Yeah, that's
it's true.
okay.
Yes. Yeah. So you consider the trajectory of the Brownian motion, and it still have these properties. Yes. Okay. Now the self-intersection, the local time will be used to describe some way the time spent by the trajectories of the Brownian motion at these points of self-intersection. So self-intersection, local time. Okay, so the local time at these points of self-intersection. Okay. Now the definition of self-intersection local time is given by as follows. The local time of self-intersection that we will denote by rho k is the local time of the following stochastic process. It is a huge stochastic process that contains these increments, and just maybe in a few slides we will understand why we consider these increments and how the local time will describe the behavior at these points. Okay. Okay. So k here to indicate the multiplicity of the points. So this self-intersection local time will be important to describe the behavior of the trajectories around the points of which are k multiple points. Okay. Now we just have to rewrite the definition of the local time, but for this new stochastic process.
So we can clarify, probably I just missed these points, T1 to k, they are the points of where we have the self-intersection.
No, these are all the possibilities of.
All
Yes, yes. So this huge process contains all the increments, but of course, when this process is equal to 0, imagine that this vector is equal to 0, then of course what does this mean? It means that xt1 is equal to xt2, equal to xt3, and so on. So it describes points of multiple points. Okay. So in fact, the local time at 0 of this process is important. It's the value at 0 of the local time which will be important. Okay. So we just have to adapt the previous definition to this new huge stochastic process, and the definition. Okay, if we use occupation measure, then we can define that. Okay, now this new stochastic process lives in Rd to the power k minus 1, and we define the occupation measure exactly in the same way that we did. Okay, so mu k of a Borel subset here will be the integrand indicator d of this process, and we integrate over all the possible t1 less or equal than t2 and so on. So what does it count? It counts all the times t1, tn, such that these increments xt2 minus xt1 and so on will belong to the set D. And if almost surely this measure has a density, then we call this density the local time of self-intersection of multiplicity k of the process. Now, just small exercise, don't be afraid. Just write the occupation formula for the local time of self-intersection. We have seen how to write.
Can you?
Yeah.
Yeah. Okay. All right. So your delta k sometimes when you in high dimension, your delta k may have something wrong when you are close to this
to the
diagonal.
To the diagonal, yes, of course. Maybe as we will see.
You may avoid that.
But
Yes.
the k not m in the delta k definition on the right hand side of the
TK.
Yes, delta k.
Yes. It should be tk, yes,
Yeah.
tk, yes. Of course, I will say something about yes, renormalization and so on. Okay. And now, of course, we have seen yesterday how to derive this formula, occupation formula, from the definition of occupation measure. So it's not difficult to derive the same formula, but for this new occupation measure. Okay. Also, we have seen two conditions for the existence of local time for any process, and it is just easy to just adapt these two criteria, but for this huge stochastic process. By the way, we will use these conditions, and the answer for this second exercise will be seen in this lecture. Okay. Now, just a small question. What does the value at 0 of the local time of self-intersection describe? And that's what I was speaking about. Yesterday I tried to explain what the local time exactly describes. But now what the local time at 0, what does it really mean? Okay. So suppose that this measure has a density, so mu k of d, suppose that it has a density, so it will always have this expression. So integral over d of rho k. So this is the self-intersection of the time. We want to understand what does it mean, the value at 0 of this of this density. Of course, if we suppose that this density is continuous at the point 0, if it's continuous at 0, then rho k of 0, as we have done just yesterday, this will be like mu k. We have just to take a small ball here, okay? Mu k of a small ball okay, around 0, and divide this by the Lebesgue measure of that point. But this is of course like yes, a limit when epsilon tends to 0. So this should be understood when epsilon is very small. This is like, yeah, when epsilon tends to 0, okay? When epsilon is very small. Okay? But let's see what does this mean now for this new process. Mu k, it counts the time that the increments xt2 minus xt1 until xtk minus xt2 minus y is here. But what does this mean? It means that it counts the time such that so if the increments are in this ball, it means that they are very close. Okay? So it counts t1, tk, such that xt1 is very close to xt2, and so on. Okay? Of course, this is an heuristic Rapting expression, and we divide by the volume of this small ball. Okay. It means that this value at 0, it counts the time of multiple points. How much time spent in points of multiplicity k, but of course compared to the small, in infinitesimal small neighborhood of these points. So imagine that we have a lot of trivial points, so we count how much time spent in very small neighborhood of these points, and we divide this by this the measure of these small neighborhood. This ratio will give us this this value okay at the point. So the value of the local time at the point 0 is important, and it describes the time spent around these points of self-intersection. Okay. Now, just the second definition that we can put for the self-intersection local time, the first one was obtained by the density of the occupation measure, but another one can be also obtained by kind of approximation, exactly like we did with the local time. So we define here this random variable t epsilon k as the integral over delta k of this product p epsilon d xtj plus 1 minus xtj. It is okay. It is similar to the just let me go back a little bit. It is similar to, of course, to this kind of approximation. Okay, but just we have to adapt this to this new stochastic process that contains the increments. Okay. Of course, we can put also minus uj here. We can put some points from RT, but okay, the limit of this now will be the value at 0. As I said, it is very important, this value of the local time at 0. So we can investigate the existence of the self-intersection local time either by checking the existence of this density or by checking the existence of a limit of this family of approximation. Okay. As a first example, we'll check the Wiener process, the Brownian motion, and it was proved that the d-dimensional Brownian motion has a double intersection local time. Here we will concentrate on k equal to 2. So we will look to the double points of the Brownian motion. And it happens that the self-intersection local time only exists when the dimension is less or equal than 3. Moreover, this density has a continuous version, and it is continuous in the whole space Rd, but not at the point 0. And we will see later how it behaves around this around 0.
I have some problem about the high dimension. By high dimension, I mean the dimension is equal to 2 and 3. In this case, if you are delta, so this is still, for example, the triangle contains the diagonal, then it blows off this limit.
Yes, but here the self-intersection over time is like it is the density of the occupation measure, but the self-intersection over time will be the value of this density at 0. But the value at 0, we will see later that it is infinite.
Okay. Yeah. So your intersection local time now is not limited to the point 0.
Yes, not limited to the point 0.
I see. I see.
Yeah. It's like a global result. Then the value at 0 will be described later.
Okay.
Yeah. Okay. So here I will try to make a part of the proof of this result because it can be accessible to not such a difficult using the techniques that we have seen. So we will denote by xi t1 t2 this process bt2 minus bt1, and we'll try to check that this measure has a density.
By doing this kind of a characteristic function, I guess you try to prove characteristic function.
Yes.
Is a square integrable.
Exactly.
Okay.
Exactly. It is this criteria here.
Yeah.
That we will try to adapt. Yes, exactly. So even the answer to this second exercise is already here in this proof. So how to prove this result? So we consider this new stochastic process, and just here I recall some formula about the characteristic function of Gaussian vectors. If we consider a Gaussian vector with the mean vector denoted by M, variance matrix denoted by A, then the characteristic function is given by this formula here. And if this vector has independent coordinates, then this characteristic function has the following. Of course, in case of independent coordinates, the matrix A will be diagonal, and this product, inner product here, will give us exactly this sum. Now, a small exercise that will be needed in the proof. Check that if B of t is a one-dimensional Brownian motion, and we have S1 less than S2 and T2, then the variance of this difference between two increments is given by T2 minus T1 plus T4 minus T3, but these denote T with index parenthesis 1 is the minimum of these 4 times, and T with index 2 is the second one. So, okay. So if we order these 4 times, then we obtain T1, T2, T3, T4, and it's not a difficult exercise. We already have seen the definition of the Brownian motion yesterday, and the properties of the increments, the independent increments, the stationarity of increments. So it's not such a difficult task to check this the value, this variance is equal to this formula. Okay. Now let us go to the proof. Checking exactly to prove the existence of the self-intersectional time, we will check that the occupation measure is square integratable, and the criteria is exactly this one. So we have to check that the integral over RD and integral over delta 2, again integral over delta 2, and the expectation of this expression is finite, but of course it seems to be a complicated integral, but it can be computed. First, this is clearly the characteristic function of this random vector here, and it is a Gaussian vector, xi t1 t2 minus xi s1 s2. But of course, always, what is xi? It is bt2 minus bt1, and of course the Brownian motion has independent increments. So this vector here is a Gaussian vector with independent increments, and the covariance matrix will be diagonal. But what it contains in the diagonal, it contains these values here that we already have obtained in this task. Okay, so this characteristic function is exactly given by exponent minus the norm of theta squared divided by 2 multiplied by this. And now if we integrate over Rd with respect to theta, what is the value of this integral? It will be some constant d, maybe 2 pi to the power minus d over 2. And we will have in the denominator the square root of this expression actually. So now we need to check what is the necessary condition on d such that this integral here is finite. Of course, again, these t1, t2, t3, t4, these are like order statistics, okay, for S1, S2, which is in delta 2, and T1, T2, which is in the other order. So we have delta 2, and we have an interval here, we have T1, T2 here, S1, S2 here, S1, S2. It is like that we have, say, T1, T2, and we have, let's say this is 0, and we have S1, S2. There are different possibilities how it is located, the second interval. It can be here, S1, S2, or here. There are many different possibilities. I really want to make this proof. It's not such difficult, but you will have an idea about this kind of integrals because it appears a lot in the investigation of self-intersection. Okay. Now, of course, for example, if S1 is here, S2 is here, then this will be equal to T with this index. This will be T with this index, and so on. Okay. So there are different possibilities, and you can divide all the six. There are 6 in fact possibilities according to the position of these two intervals. Okay, but they are like each pair of them. They give the same anchor. I mean, if we have this position, S1, S2, and T1, T2, and if we had this position, so T1, T2, and we have S1, S2 like this. these different possibilities, these two different situations will give the same integral because of the symmetry between S1, S2, and T1. So at the end we will get 3 integrals mainly. So the first integral will correspond to the situation T1, T2, and the two intervals are non-overlap. Okay. The second one will be they will have intersection. So let's say like this, S1, S2, and the third one is included in the other. T1, T2. So we will try to compute this multiple integral in each of the following 3 cases. Okay, so E1 will denote the first integral corresponding with the first situation, and E2 and E3. Okay. Okay, I will show how to compute E1, but the 2 others can be done in the same way. Okay, so we have integral over S1 less than S2 less than T1 less than T2, of course between 0 and 1, and we have we integrate with respect to S and T, and we have in the denominator C2 minus T1 plus S2 minus S1 to the power D over. How to compute this integral? We can make a change of variables. X1 is equal to S1. This change of variables can be obtained from here. Just follow the order. Okay? So X1 is S1, X2 is S2 minus S1, and then T1 minus S2, and so on. Okay? But if we write it in this way, we will have this integral will be transformed to the following integral with x2 plus x4 to the power d over 2. It is more simple. Okay? And we see that the variables x2, x1, and x3 do not appear, so we can integrate with respect to these variables first. And what we obtain is the following integral over x2 plus x4 less than 1, and we have this expression. But now we like we do another change of variables. Okay, we denote by u the x2 and the x2 plus x4. So this integral here will have the following form: 1 minus v squared, and in the denominator v to the power d over 2. Since u does not appear, we integrate first with respect to u, and when integrating with respect to u, we will have v, because u varies between 0 and v, and the final integral will be 1 minus v squared divided by v to the power d over 2 minus 1. The integral, this multiple integral, is not such complicated, but it's important to follow it to the end, because there is a dependence with respect to the dimension, and one have to be careful, okay? Because it will give us a condition on the dimension. Now we can see that when this integral is finite, it is clear that if and only if d over 2 minus 1 should be strictly smaller than 1, and this gives us this condition. Okay. Okay. So now we have this result, that the double intersection of the time of the Brownian motion only exists when the dimension is less or equal than 10. Okay. The following results describe the behavior around the origin, around 0, and in dimension 2, because we have seen that the density exists. It is continuous in Rd, but not at the point 0, and these two results explain how it behaves exactly around 0. It is important because, as I said before, the value at 0 really has a good meaning with respect to these points of self-intersection. Now, in the planar case, means that if the dimension is equal to 2, then this density of 2 of u, if we subtract this expression here, then the limit will exist almost surely and in N2 sense. But does this mean means that it means that, okay, here dimension 2. So we have this rho 2 of u minus 1 over 5 log L 1 over the norm of u. It converts to some fixed random variable when u tends to 0. And so, of course, this quantity here, it is clear that it goes to plus infinity when u tends to 0. And so, we deduce that this density, this self-intersection local tower, it also tends to plus infinity when u tends to 0. Okay? We can deduce u. Okay? Like this. When u tends to. So, the value at the point 0 is infinite, which means that the local time on the points of double points for the planar linear process is infinite. Okay. And in three-dimensional case, from here again, the limit of all this expression exists in N2 sense, so there exists a random variable such that this converges to that random variable when it tends to 0, and this means that d equal to 3, we have that rho 2 of u will be like when u tends to 0, some random variable multiplied by the square root of the log f, and then plus 1 over. Okay? And of course, this is a quantity that blows up, that tends to plus infinity when it tends to 0. So again, the value at 0 is infinite, and it is these asymptotics explain how it tends to plus.
So I remember that's the difference between 2 and 3 is 3 actually the limit is Gaussian, and 2 is a
constant.
Yeah,
Here the limit is in fact a constant.
That's called renormalized self-intersection for that side.
Yes.
Non-Gaussian, but for the 3,
It's complicated. Yes. 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 This property leads to a redefinition of the self-intersection local time. We can redefine in such a way that this rho 2 of u does not go to plus infinity. Okay, and this is called by a renormalization procedure. So instead of taking these times in delta 2, this is delta 2. Yes, t. This is the set s less than t. Okay. So instead of taking it on the whole set, we divide it in such a way that we can avoid we try to avoid the diagonal because if we are close to the diagonal, then this problem of divergence will happen. Okay. So what we will try to do is to try also to find the self-intersection over time bar for this specific class of Gaussian processes that I introduced also yesterday, called by Gaussian integrators. And okay, maybe if we avoid to recall the first definition, these Gaussian integrators are simply stochastic processes given by expression of this form. So it is an integral from 0 to 1. Here A is a bounded linear operator in L2 of 0, 1. And this is an integral, a Wiener integral with respect to the Brownian. Okay. And we have seen also some examples and some properties of this kind of Gaussian processes. We also have seen that this process has a local time if the operator A is invertible. It happens that if A also is invertible, then this process has a self-intersection local time as a limit of this approximation. Okay. And the proof also here is not such a difficult, you can at least make a proof in the case k equal to 2. So okay.
Yes.
Okay.
Okay.
So before the proof, let me recall some property. The covariance function of this process, this Gaussian integrator, will be given by the inner product of A indicator 0s and A indicator 0t. And from that, okay, another exercise is check that the covariance matrix of the vector, the following vector of 2 increments, will be the Gramian matrix of these two functions, A indicator S1, S2, A indicator T1, T2. Of course, covariance matrix will be not such difficult to compute. You already have this basic covariance function you can use to compute the variances and the covariances between these two increments.
Of course, by look at this, natural thing in my mind is to think fractional Brownian motion. Is this included as a special case?
Yes, the fractional Brownian motion is an example of the integrators, but when the Ernst parameter is
Bigger or equal to 1/2.
yes, bigger.
Bigger or equal to 1/2 of the positive Brownian motion.
Yes,
So
because yes.
you define also A property, so this will be a representation of fractional Brownian motion.
Sorry.
So my question is, I hope that if you by define this A operator properly, and you get this x of t to be a fractional Brownian motion, is that possible?
I don't think so. But we use some characterization of this class of processes, and this characterization does not require to determine the operator A.
So can you give us one of the well-known or something we know example that this creates a kind of a Gaussian process?
If this operator is an isometry,
Okay.
this will the process will be a Wiener process.
Well, that's
But okay.
But he said that fractional Brownian motion is also an example.
Example. But
Yes, it is example.
Okay, so.
He says that he doesn't remember how this is.
But the operator, we don't
okay.
know exactly
Yes,
the
but so this is a
expression.
representation for fractional Gaussian motion as a stochastic integral with respect to Gaussian motion. But the integral is not a nice function, probably. I have to check, but it's like a power function, which probably not that well determined. I have to check.
Yes, there are representation of fractional Brownian motion as a stochastic integral.
Or Louisville, or some Louisville process. Maybe that can be different as well. Yeah, that's the main part of the fractional branch.
Yes, the main part, okay.
Yes.
Yes, yes.
Okay.
Fractional Gaussian motion should be integral from minus infinity.
Yeah.
Yes. For example, okay, the Brownian motion and the Brownian bridge, we can derive easily the correspondent operator.
Okay.
Okay. But, maybe also for Ornstein-Uhlenbeck process. Not so sure. Okay. Okay, so now the covariance matrix of this
There is some representation goes from 0 to with the bad function.
Immediate fraction.
Yes.
But he mentioned that that's a part of that, so that involved the integration from negative infinity.
Yes, yes, yes.
So that's
Yes. One is one from this is from minus infinity. I guess there's some problem. Sorry.
okay. So now that we have computed this covariance matrix, of course it will be used because we have some criteria that uses the determinant of the covariance matrix. Okay, now for the proof, only in case k equal to 2, so adapting the criteria that with the square root of the determinant of the covariance matrix, what we have to check is that the following integral is finite. Okay, so here we have the determinant of the Gaussian matrix, the denominator, and here we will use a very nice inequality given by the following law. So if A is a bounded and invertible linear operator in any invert space, then for any k, there exists a positive that only depends on k, such that for any k vectors from H, we have the following inequality between, okay, J here is the Gaussian determinant, okay? The Gaussian determinant of these vectors and the Gaussian determinants of the vectors without.
So your H is L2
Yes.
others, one L.
Yes.
Okay.
It will apply it, of course, of group 0, 1. We'll apply it exactly here for this determinant, Gaussian determinant here, for this AE1, AE2. But the inequality is more general, so it is maybe good to know this inequality, and even I have a good proof that I will keep to the end. Okay. Now, using this inequality, of course, this determinant here of the Gaussian matrix will be greater or equal than some constant, and the determinant of the Gaussian of indicator S1, S2, indicator T1, T2, without A, we can remove the A using this inequality. Okay. So it is so enough to check that this determinant is finite. Yes, exactly. Gaussian of indicator S1, S2, indicator T1. We can remove the A using that inequality, and here again, we will divide this multiple integral in 6 integrals. Depends on the position of S1, S2, and T1, T2. Okay. So we have at the end 3 integrals to compute, and they are not so different from the integrals that we have been discussing. So we have an integral of S1, 2 non-overlapping intervals, and the second one they are overlapping, and the third integral, one is included into the other. So if we take the first one, so we have this integral here with d2 minus d1 is 2 minus s1 with square root, and we want to prove it is finite. The same way as before, just make this change of variables. This integral will be square root here x2, x4, and it is a finite. Okay. The same thing, or maybe E2, when the 2 intervals have a small intersection, then we will have the Gaussian determinant. We can check that to be equal to this function here, this expression here. Okay, and again we do the same change of variables, and we can transform this integral to the following. We find exactly that is the following integral, and this is finite exactly as in the previous one. Okay. Also, the third one. Now, if one interval is included into the other, the Gaussian determinant will be given by this formula here, and we can make a change of variables, you see here, and we will obtain also this finite integral. Okay. It's not really difficult to check these calculation. Okay. And now, so we have proved that this condition of finiteness of the integral is checked, and so we have this self-intersection global time. This is in the case k equal to 2. For larger values of k, the proof is in fact longer and needs more material. Now, just for this lemma, here, this lemma, I try to also present its proof. It's not. It's also accessible to students. Will be done by induction. Okay. But first. Let me recall that since the operator A is invertible, then we can find constant small m and capital M, such that the norm of AX is bounded from below by m times the norm of x, and from above by constant capital M times the norm of x. Okay? Invertibility is up here. Continuity is up here. And now, if we have a closed subspace, then we can check that the distance between AX and AF, X is any vector from the interspace H, will be greater than this constant M times the distance between X and A. Okay? You can check it through these argument here, and now using this we can now prove this inequality by induction. Okay. If we take just one single vector, of course, what is the Gaussian of AE1? This is simply the square norm of AE1, which is clearly which is of course greater or equal to m squared times the norm of E1 here squared. And we have the result for just one vector. Now, if we suppose that we have this inequality for any family of k vectors, and now we consider k plus 1 vectors from the Hilbert space H, and we will denote by F the linear span of E1, Ek, then, of course, there is a formula, I think it is known by students, about the Gaussian determinant. The Gaussian determinant can be used to compute the distance between a vector and the subspace. Okay? Mainly, the Gaussian determinant of k plus 1 vectors is the distance is equal to square distance between the last one and the subspace generated by the others. Okay? Multiplied by the Gaussian of the first vectors. Okay? So this is a property, I think it is known about Gaussian determinant. And now just we apply this hypothesis here, and the inequality that I have just shown in this first part, we can find a new constant that only depends on k times the Gaussian determinant of E1, Ek plus 1. So, that's all I have today. Okay, we'll continue. Thank you.
Yes, I have a question. I'm so interested of Naoufel Salhi 2018. So we consider Gaussian integrators such that A is invertible. So what are the examples of such integrators with invertible A, but not isometry?
Yes, convertible A, but not isometry.
So no Brownian motion, but some other.
Yes, Brownian motion.
Like a Brownian bridge with the K?
No, there are examples.
Yeah.
There are examples, of course, of invertible operator, and maybe I plan to give some examples in some other results, but I can tell about something. How to construct an invertible operator. You can take, if you take any operator, B, so the norm of B is smaller than 1, and then you take A to be identity plus B, then it is invertible. That's one. Also, if you take the norm of B to be smaller than 1, you may take the geometric thing. Yeah.
This is exactly
Yeah.
this is inverse to identity plus or minus B, okay, plus and minus B.
And I even will give some concrete examples. Okay. So, for example, here, remember that if you take B to be the Volterra operator, I take this one. Okay. DDT, but yes. Then I think it's now a bit smaller than 1, and then we can find even an expression of this. Yeah, can find even an expression of this invertible operator. It's one of the examples that we can consider. But of course, the associated operator, I even plan to give explicit formula of the associated operator, but they are not such. The associated integrators, but they are not such familiar or known processes.
So like typical processes.
Yes, yes. Typical processes. Maybe, for example, yes, it's not general. The operator is not. No.
So you're maybe concerned about your computation about this determinant in this result. Oh, okay, just one of them. So I have a problem about the notation. So this is a determinant of the covariance matrix, or
Yes. The determinant of the covariance matrix.
determinant of covariance of what? GR, I don't know what's that.
The Gramian determinant.
Huh?
The Gramian determinant.
Oh,
The Gramian matrix. The Gramian matrix. Okay. So you.
okay, so perhaps I missed that.
Yes.
Could you please justify it?
So the Gramian. There is the matrix where you put E1 and E1
Oh, I see.
and so on.
So this is not wait.
Yes, we have operator which is stochastic
Right.
integral. This is the integral.
Okay, I see.
Yeah, so like it was on
I see. So the point I try to see is maybe that's really relevant to your computation. Let's say if you wanted to compute covariance matrix, you can assume that the covariance matrix was generated by Gaussian vector, right? Even that sometimes it's not Gaussian. You can assume that's be generated by Gaussian vector. Then the determinant can be written as a product of this what we call conditional variances.
Yeah.
Sometimes, of course, in your case, since your matrix is only 2 by 2.
Yes.
Let's say you have n by n, then that may simplify a lot about this computation.
Yes. This product of conditional.
Variance.
Yes. I think this is used in local non-determinism.
And then other places.
Yes.
Okay. That's all remark I want to make.
No other questions? So as you can see here, you can find some modern results, and you can see that you can somehow touch modern mathematical and modern problems. And if you are interested in something, please come and ask questions, and I'll try to solve exercises. Maybe we'll have some questions later tomorrow or day after tomorrow, so we can discuss them as well. So then for today that's all. So let's meet tomorrow, and we will have a little bit
not a little bit, but just 1.5 days.
yes, we will have longer lectures, because on Friday we have no electricity here, but we start at 9 in the morning, so
Please come and ask questions.
I will.
Thank you.